Welcome everyone to next year's CPPC seminar. So it's my pleasure to introduce Judit Pérez-Romero, who's coming to us from University of Noga in Slovenia. So Judit originally did her PhD with Miguel Sanchez Conde in the IIT in Madrid, and she's really an expert on gamma ray searches for dark matter. And that is what she's going to tell us about today. She's going to talk about some gamma ray searches for dark matter in galaxy clusters. So I'll leave it in your hands, Judith, and pass it over to you. Thank you.
Thanks a lot for the introduction and for the invitation, Karen. So yeah, this is who I am. My name is Judit. Currently, as I just mentioned, I'm a SMASH postdoctoral fellow in University of Nova Gorica. And if you're in the job market this year, just to mention that the third call for the SMASH postdoctoral program it's open. And if you're interested in it, you can ask me later or just send me an email and I will be happy to guide you through the process you are interested in applying for. But for now, today I prepared this small seminar where I plan to basically give a brief summary of the status and the prospect on which is the current status of dark matter gamma ray searches, specifically when we try to look for it in galaxy clusters. So it's not new to us that we have plenty of gravitational evidences at different scales in the universe about this strange component that we seem to be that appears to be at all of the different scales some kind of missing mass, like the one that we found when we try to measure and fit the rotational curve of spiral galaxies and galactic scales, but we also find this same kind of missing mass at the scale of galaxy clusters, for example, when we measure peculiar velocity flows, but not only that, because this kind of mismatch also appears in every kind of mass tracer that we use to approach to measure the mass of a galaxy cluster, because mass of galaxy clusters are not especially well defined, but not even in the things that we consider as astrophysical objects, but this kind of evidence also appear at cosmological scales when we try to measure the component parameters of the universe through the fitting of the anisotropies of the cosmic microwave background. So according to this last fit, basically what we know is that there is something that we call dark matter that amounts more or less up to 30% of the total energy budget of the universe, that it's not only to blame for the different puzzles that I've been showing you before, but it is also embedded and very, very embedded in how we understand the universe has evolved and how the different structures, the different astrophysical structures that we see were formed. And this is why we have this DM part, this CDM part in the name of our standard cosmological model, which is lambda CDM. So according to lambda CDM, so according not only to these mismatches, but also to the results and according to data, observational data, what appears to be is that this dark matter is basically the one that drives the formation of all of these different structures in a kind of a bottom-up kind of a scenario, meaning that in order to reproduce the structures that we're able to measure today, the evolution and the formation of these structures went from the smaller scales, and then via merging or collapse of these smaller objects in mass, we get to grow these larger and larger structures until we aim forming the kind of structures that we see today, as the picture that I attach here, which is from a very nice simulation, which is the illustrious TNG simulation. This already tells a lot on this strange and mysterious component, which is the dark matter, no? Which is how it behaves when put in a context of gravity, which is basically the one driving the dark matter interaction, because it's the only one that we, for the moment, have been able to measure, no? And this tells us that according to this map, basically we can distribute and we can distinguish between the larger objects that we are going to call halos of dark matter, that basically are the host of the brilliant structures, of the shining structures that we see from astrophysical objects, and then some smaller objects that are going to be the relics of these bottom-up formation structures that basically are smaller subhalos that are in the gravitational field of these larger halos. This is going to play a role in the future, in the next slides. Even though we know a lot, or maybe even though we know these things about dark matter, it's true that in the sense of the fundamental nature of what dark matter is, we still have plenty of room to play. And we have a wild slew of candidates of dark matter ranging from a very wild range of masses, starting from 10 to the minus 22 electron volts in the candidates that we call fuzzy dark matter, up to the other part of the ground where we have non-point-like objects like primordial black holes. But for today, I am going to focus in one specific candidate, which are weakly interactive massive particles. Weakly interactive massive particles are some candidates that come from theories beyond the standard model that have masses between 1 GeV and a few hundred TeVs that by construction, their masses match perfectly and the relic abundance match perfectly the one that we are supposed to measure with the cosmic ray, with the CMB. And not only that, we have this so-called WIMP miracle, but then about WIMPs, they are also extremely interesting because we expect them to have a very weak interaction with the standard model particles. That means that we have an open room, we have a possibility of detecting dark matter through other channels that is not gravitationally. And in fact, we have three different ways of looking for these particles, for looking from the WIMPs. We have the production in colliders, meaning that we're going to find is to go from two standard model particles, then they interacting and producing one dark matter particle. This is the case that it's from, for example, in LHC. Then we have collision, which is so the way that direct detection approach to this problem. Basically, we expect dark matter particle then interacting in the halo of the Earth, basically interacting with one standard model particle, and then from the missing energy be able to say something about this dark matter particle. And then the one that we are going to cover today, which is indirect detection, which is through the process of annihilation or decay of dark matter. So basically, what we are going to assume here is happening is that we have some regions in the universe, like the ones that I defined before. So basically, halos and subhalos, when we know this dark matter is more concentrated, that basically can trigger the process of annihilation of two dark matter particles into standard model particles. Okay, so through this process that is going to remain as somehow open because there are different kind of models that can basically detail the kind of process that we hear, but we want to leave the room sufficiently open. There are three main channels that are going to help us to look for these winning candidates, which are gamma rays, neutrinos, and antimatter. In the case of antimatter, this is like a smoking gun. We don't have a lot of antimatter from any other source in the universe. So basically, this would be a triggering smoking gun. The problem with antimatter is that these particles suffer from deflection from the strong magnetic fields that these particles encounter from the place of annihilation to when we are able to detect them in the Earth. So this is a complicated problem to solve. And then we have gamma rays and neutrinos. Both of them are not very interacting, which is actually good because this means they travel the universe in a straight line. And the problem with neutrinos is that they are too much complicated to detect even for us in the Earth. So in this sense, gamma rays are still looked as the golden channel for the indirect detection techniques. So now we have our target, the dark matter. Now we know how to look for it, but we need to know where. and we were talking about these halos and halos. So let's try to make a list of the different places in the universe that are good targets to look for this dark matter. So the first that we will need is to find a place with very high dark matter density, because the flux that we receive from this annihilation or decay of dark matter is either proportional to the square of the density profile of the dark matter object, or linearly dependent in the case we assume this dark matter particle can decay. Then we also want very massive and nearby objects, because again, the flux is going to go proportional to the mass of the object. So the most massive, the better. And then as close to us as possible, because the flux is going to decay as 1 over the distance squared from us. And then it will be amazing is this astrophysical object will not show any other kind of astrophysical emission in this energy range that we are looking for the WIM. So basically having a very low or completely negligible astrophysical background. Unfortunately for us, this object still has not been found in nature, but we have plenty of other objects that are complementary between them, and all of them are worthy to explore. And among them, so just mentioning a few of them, we have, for example, the galactic center, which is extremely high in dark matter density. It's the closest object for us to look for. The problem is the astrophysical background that we expect us in the galactic center. Then, for example, another very known candidate are dwarf spheroidal galaxies. In this sense, dwarf spheroidal galaxies, for example, we don't expect any other astrophysical counterpart in terms of emission. So that kind of objects are also very good for look. But I'm going to look today through the case of galaxy clusters. So galaxy clusters are the largest gravitationally bound structures that are formed by gravitational collapse. They have masses of the order 10 to the 14, 10 to the 15 solar masses, and their mass, basically up to 80% of the mass of a galaxy cluster, is in form of dark matter. What does this mean? That we have a very massive object with very high dark matter density, and it's true that we can find some of them that are very close to us, that are in what we call our local universe. What this means in terms of gamma ray indirect dark matter searches is that for the case of decay, so this dark matter particle decaying into standard model particles, galaxy clusters are the best possible targets to consider, since the flux is directly proportional to the dark matter density, and this is the most massive object that we can find close to us. And then in the terms of annihilation, we will see that they can be competitive to other prime targets, like, for example, dwarf spheroidal galaxies, in terms of the amount of gamma ray induced flux from these dark matter annihilations. However, also from galaxy clusters, we expect a counterpart in gamma ray emission from astrophysical process. And let me explain this a little bit more into detail. So up to 80% of the mass of a galaxy cluster is in the form of dark matter, but the rest is divided basically into two different kinds of baryonic matter. The first one is the least important one for us, which is basically the mass which is divided through galaxies that are forming the galaxy cluster, and the rest, up to between 15 to 17%, is in what we call the intracluster medium, which is a extremely hot and dense plasma. This means that the situation that we have is that even though we used to think of clusters as virialized objects, in reality, we can find clusters with a lot of activity, because some of them, as they are the largest structures, they are still going through merger events between one or the other, or still accreting some galaxies. Then we have the feedback from the same galaxies and agents to the different components in mass that we have in the galaxy cluster. They have very strong magnetic fields, and all of this produces a lot of turbulence in the ICM. And at the end, all of these different processes and acting as acceleration mechanism and producing what we call as cosmic rays. In fact, as it's shown in the picture shown here, from the Chandra and XMM data from the Perseus galaxy clusters, we have detected cosmic rays in the direction of galaxy clusters, specifically leptonic cosmic rays. Specifically, this picture, I think, is the one that's coming from diffuse synchrotron emission. But we do not only expect leptonic cosmic rays to be produced, but also hadronic cosmic rays. And from the hadronic cosmic rays and then subsequent decay into the pi zero mesons, and then the subsequent decay of the pi zero mesons to gamma rays, we also expect gamma ray emission from this process of cosmic ray acceleration in galaxy cluster. And I say expect here because despite all of the effort that has been done in the past, let's say, 10 to 15 years, we have been looking for this diffuse gamma ray emission coming from either astrophysical or, of course, dark matter processes in gamma rays, but neither of them have been detected. So only the fact of being able to robustly see a diffuse emission in gamma rays in galaxy clusters would be a supermassive hint in the very high energy astrophysics community. Here I leave you an incomplete list of the different works that has been done in the past 20 years, in fact. I see the first one here by Olaf Reimer, where basically we can see a tendency of not being able to find gamma ray emission, whatever the source of this emission was, but especially in the last years, especially from the works that are related to the Fermi-LAT, we see a tendency of start seeing some hints of my signal of this gamma ray emission. Again, whether it may come from dark matter or this expected astrophysical emission from cosmic rays. So what can we do in this scenario? In the present, we have the satellite Fermi-LAT. Fermi-LAT satellite is a gamma ray telescope that operates in the range of 400 MeV to 1 TeV, having the best sensitivity at 200 GeVs. And the best thing about Fermi is that we have already 16 years of all sky data available to analyze, which is amazing. And then what we can do for the future, because with Fermi-LAT, a lot of studies has been already made. Of course, we need to keep exploring the possibility of using the Fermi-LAT data, since data is here and it's of tremendous and enormous quality. But for the future, we want also some complementarity. And this is what the Cherenkov Telescope Array Observatory will provide in the very near future. So CTAO, it has the first telescope already in operation since 2 years ago. And the energy range is complementary to the one that we have in Fermi-LAT for Fermi-LAT data, because it starts at the range of more or less 20 to 30 GeVs and has a good sensitivity until more or less 100 TeV, having the best sensitivity at 1 TeV, which is basically where Fermi-LAT stops being sensitive to the emission. And they are complementarity because if with Fermi-LAT we have 16 years of all sky data, with CTA what we will be able to provide is deep dedicated surveys for specific galaxy clusters that we want to explore in more detail. So this is what we have been doing. So let's go directly to the first case, which is the present, which is the work of constraining dark matter contribution of gamma rays in galaxy clusters with Fermi-LAT. I already introduced Fermi-LAT, so I will not explain a lot much about it. So basically, it's a satellite-based telescope that was launched in June 2008. And the important thing here is that it operates in all sky mode. So basically, we have a whole image of the sky every 3 hours. And we have this amount of data over the 16 years of operation of Fermi-LAT. Here are the performance capabilities, as I just mentioned. Here the sensitivity peak, so basically around 1 GeV. And here the the angular resolution of Fermi-LAT, which we see it's not competitive to other kind of telescopes, because it's we can see we reach this plateau here around 0.1 degrees for the best sensitivity, for the best angular resolution that we have. So coming back to clusters, since with Fermi-LAT we don't have constraints on observational time, this means that we can build a sample of the best galaxy clusters for dark matter searches, because we don't have the constraint, and this is amazing. So what we did basically is to establish some selection criteria and then try to form this sample of the golden galaxy clusters that are the best possible targets to think about in terms of the amount of gamma ray induced flux from the dark matter annihilation and decay that we expect from these clusters. So the first thing is that we need to know it's basically to have a cluster that we have an estimation for the mass, because the model that we are going to produce to estimate this dark matter induced flux, this gamma ray induced flux, is starting from the value of the mass of the clusters. And then, of course, we know we need local galaxy clusters again to not lose the flux due to this dependency on 1 over the distance squared. And then we also decided to avoid the inner galactic plane, to avoid this galactic diffuse emission in our data, and then to avoid problems with overlapping regions. We also required our clusters, the center of our clusters, to be separated at least 2 degrees, to be able also to account for the cluster extension. That is going to be very important, that I will show you later. So with all of this information together, basically, we went to the most known galaxy cluster catalog that provides masses in X-rays, so basically for local galaxy clusters. And we find the heat flux catalog with these different characteristics, but it has some observational inconvenience. And as you can see, the catalog is from 2002, so we wanted to update it. So basically, we updated the heat flux catalog and complemented it with the clusters that were used in previous searches from the Fermi-LAT collaboration. This was the work from Fermi-LAT collaboration in 2010 and the one in the 2014. Sorry. So with all of this together, we end with a sample of 49 galaxy clusters. I show here a glimpse of the clusters that we think that are going to dominate our sample, because basically they are the most massive ones. Here the color represents the mass. Here I show also the mass that we put in the galactic plane, and we see some names of clusters that we know and very known. For example, Virgo, Hydra, Centaurus, Fornax. Just a glimpse of how our sample looks in the sky. And now we need to go to the modeling part. So again, our model starts from the value of the mass of the galaxy cluster. And for computing the dark matter-induced gamma ray flux from any astrophysical object, in the case that we are assuming here, which is basically weakly interacting massive particles, we are able to factorize our computation into 2 different terms. The first terms that correspond to the particle physics model that basically encodes all the information about the spectral shape of the signal. So basically the mass of the dark matter particle, the annihilation cross-section, and the specifics of the spectrum and how it looks. And then we have the astrophysical factor that basically encodes all of the information related to the spatial shapes, to the morphology of the expected signal. To mention this now and not in the future, basically all of the computations related to the astrophysical factor that I'm going to call J factor in the case of annihilation and D factor in the case of decay, passing on using this free software that I really recommend in the case you need to compute astrophysical factors, which is clamping. So basically these astrophysical factors, either it's annihilation and decay, are dependent basically on the dark matter density profile of the object. So basically how we model the density of dark matter in this object. In the case of annihilation, here I sketch the dependency that we have of the J factor with the parameters that we use to model the galaxy cluster, just the mass, the distance, and the concentration, which is going to play a very important role. In the case of decay, we see that the dependency is only with the mass and the distance. This means that in the case of annihilation, we need to take into account how the dark matter is clumped inside the halo. So this means that we will need to take into account the subhalos that we have in the main halo. So basically, the subhalos that we expect to find in the galaxy cluster to be in order to have a realistic or a best guess scenario for our J factors. So this is how we are going to model our dark matter densities. We start from the total amount of dark matter density is going to be divided in the smooth component, which is the main halo, and then an average distribution on the substructures, basically on the subhalos. In the case of the main halo, we are going to assume an NFW profile, so the standard Kaspi-like Navarro-Frank profile, while for the concentration mass relation that is going us to it's going to allow us to compute the parameters, so basically the normalization in the density profile and the scale radius of the density profiles are computed through the relation between the concentration and the mass. This one has been shown to provide reliable results on the galaxy clusters mass scale, because this is a problem with concentration mass relation. Some of them do not work for all of the mass ranges. This one, we checked that it's very good for the mass range that we are going to work on. And for the substructures, so it's very difficult to assess the distribution of this object. So basically what we are going to do is to provide a model on the distribution of the population of subhalos inside the main halos. This for every cluster in the 49 galaxy cluster sample that we have. So basically, this is how we also can factorize the different distributions of the population of the substructures that we expect. The first one, which is basically how the subhalos are distributed positionally, spatially inside the main halo, which we call the subhalo radial distribution, because we are assuming spherical symmetry here. Basically, you have two different kind of models that we can follow here. Basically, the first one, which is based on the simulations of Via Láctea 2, which is called anti-bias relation, and the second one, which is based on the Aquarius simulation, which is called the bias relation. But only to mention that these two parametrizations can mimic one each other depending on how it's in the parameters. The most important distribution that is going to give a very palatable difference is the subhalo mass function. Subhalo mass function, according to embodied cosmological simulations, has this form of a power law, where basically this alpha here that acts as a slope is basically going to tell the amount of clusters of different masses that we have. So a value of 1.9 will be a more conservative value, giving subhalos of larger, even more subhalos of larger masses. And then a value of 2.0 will give more clusters of lower masses. This will impact later that as the value of 2.0 will be impacted, having a larger contribution to the total J factor from the part of subhalos. And then the last part, which is the concentration that we find in these objects. And this is important because according to embodied cosmological simulation, from all of this process of structure formation, these subhalos appear to be more concentrated than main halos, and it's important that we apply a different relation from the concentration mass relation than the one that we have used from the main halos. In fact, the one that we used, developed by Molinet et al. In 2017, does not only take into account this difference, but also takes into account the change in concentration that the subhalo has, depending also on the position where the subhalo is inside of the medium. So all of this together, what leaves is a very complicated picture, because as you can see, we have a lot of uncertainties coming from the distribution of these subhalos. So the way we have to benchmark this is to define benchmark models, to try to encapsulate all this uncertainty to the expected substructure population. So we define three benchmark models: the mean, the med, and the max. For the mean model, we do not consider substructures at all. For the main model, we define what is the best guess according to the last results from embodied cosmological simulations of how much the subhalos can actually contribute to the J factor in the case of annihilation, and then the max model as an educated upper bound on, again, how much these substructures can actually contribute to the value of the J factor. So these are the results that we obtain for the case of annihilation. So basically for the mean, for the mid, and for the max model, we can clearly see a shift in the value of the total J factor here, moving from lower values for the mean model to higher values to the max model. And also what we can do is to rank the clusters that we have according to the values of J factors. And this is what is done in the plot in the right, basically. So basically, you can see that there are some clusters that are having the largest J factors. We can see these clusters are the ones that I just showed you before, that basically are the most massive and the closest clusters, like the Virgo cluster, Hydra, Fornax. So our prediction is in complete agreement with the simulation that we found. And the same, sorry, the same applies for the case of the matter decay, just with the difference that here the subhalos do not really play a role for the computation of the D factor. However, since the clusters that are close to us and more massive to us are the same, are still the ones that are dominating our sample. Another important thing about our modeling is the spatial extension of galaxy clusters. Galaxy clusters are non-point-like objects for the ones that we are going to study, because we are looking for clusters that are close to us. And this is important in the terms of how they look. For example, if we look at the sky map of the gamma ray emission from Fornax, this is what we find. This is the model that we have from the emission for the mean models of annihilation, this one for the med, and this one for the max. And you can see the effect of substructure. Basically, it becomes more relevant in the outskirts of the galaxy cluster. So this is also making more important the fact of basically taking into account the spatial morphology of the galaxy cluster, the fact that we take into account this substructure compared to the case of the minimum model where no substructures are considered. And the cluster really resembles more only the dark matter peaky model that we have as an NLW profile in the smooth part, in the subhalo part. And through this boost factor, basically, we are able to see how much these substructures contribute with respect to the bare case, which will be the minimum model. And in this case, for the mid model for the Fornax cluster, we get a boost value of 11 and a boost factor of 60. We can see how the main model provides the best guess scenario, while the max model provides, again, just an educated upper bound. We have settled everything, so now let's go for the analysis. For the Fermi-LAT analysis, we are proceeding with the standard template fitting analysis that it has been performing inside the Fermi-LAT collaboration during all these 16 years. So basically, we are using 12 years of Fermi-LAT data, because the paper came out last year, and we did the analysis 2 years ago. So this was the data that we have available. This is the energy range. We chose a quite wide region of interest, again, to take into account the extension of the cluster. And again, the standard template Fermi analysis with, we plan to do a combined analysis of the likelihood. So basically, stacking the signal of all of the different clusters and then looking if we are able to find a signal coming from dark matter annihilation or decay. For this, we use the test statistics, the TS here, but basically, naively, for the moment, we are going to assign as a TS value lower than 25, we will not be able to claim a signal, and above, we will see what we do. So just to tell you that we also test different setups for the energy range, ROI, instrument response function for the telescopes and background, and the results that I'm going to show you are basically robust against all of these changes in setup. So let's look for the TS in the different benchmark models. Here I show the combined TS in black in all of the 4 plots. The first one is where we are using the MEL annihilation model and trying to fit for annihilation from tau plus, tau minus, and here two different values of the mass of the dark matter particle. And in the lower panels, the same, but assuming decay of dark matter particle. We see in most of the cases that the individual TS, so basically all of these color ones, are far from reaching TS 25. The highest one is for Centaurus, which is close to 15, something like this. So not really something interesting going on. However, for the combined TS, the situation is slightly different, because for the mean model, which is not shown here, we do not find any signal, but for the MEL model, we do find some values for the mass, depending on exactly the channel of annihilation or decay that we feed, that shows values of TS 27, 23, 28 for decay, so values very close to TS detection 25. So what we did is to try to interpret these results as if it is dark matter signal. These are the plots that we find when we try to interpret this signal as dark matter annihilation or decay. And basically what we see is that the value of the mass that we obtain for obtaining this highest value of TS depends a lot on the channel that we are fitting, which already tells us something weird is going on, because we don't expect different values for the dark matter particle depending on the channel that we fit. And also, if we put our results and compare them to previous studies, like, for example, the study that was done in 2021 by Mattia Di Mauro about looking for gamma ray emission, for dark matter-induced gamma ray emission in peripheral galaxies, and these were from the galactic center excess, we see that our parameter space, for example, for this case, it's already in a lot of tension. And the same argument can be done for the case of decay. If you look at these different papers, basically, it seems that there is some kind of incompatibility here going on. Then, what do we do? So this analysis has been done in assuming that we have an ideal knowledge of our backgrounds and that TS is directly corresponded and properly described as a chi-square divided by 2 distribution according to the Cherenkov theorem. But in reality, we know that this is not our case, because we are using the analysis of real data, also using data for lower energies where our instrument response function is not so well determined. And we are also using extended sources for analysis, or not point-like. So how do we solve that? So basically, we build local TS distribution using 3,100 random blank sky directions to basically remove all to basically be able to compare this TS distribution to the real null hypothesis. So basically, for each ROI, we fit this specific case, which is the medium dark matter template for this specific annihilation channel and for this specific mass. Again, this is a local TS. And what we derive is that basically our TS distribution is not well described by the Cherenkov theorem. However, for this specific case, we get that our TS of 27 for the MEL model can be actually translated not to a value of 5 sigma, but to a value of 2.7. This also is the same situation for the case of decay and for the case of annihilation max. And it's true that a value of 2.7 sigma is still hint of, let's say, hint of signal, but not enough to declare a detection. So then what we do, we put dark matter constraints from the combined cluster analysis in the sense of annihilation. Here I showed you the values for the MET when we are still able to touch the thermal relic cross section here, and also for the lifetime of the dark matter particle in the case we consider decay. And now I'm going to very briefly explain what we have for the future. So CTAO. CTAO is the future of imaging atmospheric Cherenkov telescopes for very high energy. We will have two arrays, one in the north, one in the south. The telescope that is already in operation is in the north. And basically, we cover the energy range from, again, 20 to 30 GeVs up to 100 TeVs. Which is important here is that the energy range is complementary to the one that we have from Fermi-LAT, but also improving sensitivity with respect to current AACTs. But you can see that for the best sensitivity of CTA, which is reached between 1 TeV and 10 TeVs, we have up to more or less one order of magnitude improvement in sensitivity, but also a very large improvement in angular resolution. So CTA will have super capabilities to test the parameter space that is still left for wind particles, for wind dark matter particles, in the highest energy range, so above 1 TeV or so. In the case of galaxy clusters, the observation per se of a galaxy cluster is a key science project for the CTAO, because again, as I said before, it's not only the search for dark matter through gamma rays, but the detection of diffuse gamma ray emission for a galaxy cluster is a key science project for CTAO. This will be a huge milestone for the community. So in these terms, in a previous study from 2017, Perseus galaxy clusters was addressed to be the best clusters to look for in terms not only for getting this dark matter detection from a galaxy cluster, but to get this gamma ray diffuse emission signal finally from a galaxy cluster. Perseus, it's a cool core relaxed cluster that hosts two bright AGNs, one in the center, which is called NGC 1275, and another one which is southwest. And what we are going to do is basically using the latest CTAO science tools with the latest instrument response function to try to perform a prospective analysis. For the dark matter modeling, in this case, we are going to use the same kind of strategy that we have used before for the 49 clusters, but in this case, we are only observing one cluster, which is Perseus. Again, one part of the model for the main halo, the second part of the model for the population of structures that we expect to find in Perseus. Same kind of approach, NSW profile for the smooth part of the halo, for the main halo, and for the substructures, again, we are following the same procedure as before. We define three benchmark model in order to try to encapsulate the uncertainty that we have on the definition of the population that we expect in the Perseus galaxy cluster, and how much this population of structures can actually contribute to the J. Here I leave you with a table of how we define the benchmark model for this case. And as you can see, it's extremely similar to the values, to the parameterization that we have used before. These are the results that we have for Perseus. As you can see, the values that we get for annihilation for Perseus are slightly lower than, for example, the values that we have obtained for some of the clusters that we have explored with Fermi-LAT before, like, for example, Virgo or Fornax. But, for example, with respect to Virgo, Perseus is a very good candidate also because with Virgo, we have the problem that is going through a merger event. Instead, Perseus is a cool core cluster, so the modeling that we do, for example, in this sense, it will be a little bit more reliable. And we can again see the effect on the extension of the cluster when we take into account this structure, which again appears to be more and more important when we move to the outskirts to the cluster than in the inside of the cluster, because again, in the inner part of the galaxy cluster, the peak of the NSW profile is dominating. However, with CTA, the problem is that we don't have data still. So we have to simulate our observations. So this is the analysis roadmap that we are going to follow. So basically, first of all, we need to simulate our observation. And for this, we need to do the most realistic scenarios possible, which means taking into account all of the possible sources of gamma rays that we expect in the Perseus region. This means taking into account the dark matter-induced gamma rays models, as I just explained now. Then we also need to model the cosmic ray-induced gamma rays, which is something that we did not do in the case of the Fermi-LAT analysis. In this case, we did the modeling and included in the simulations, and we will include it also in analysis. But then we also need to include the gamma ray emission that we have from the truth AGNs that we have in the region of Perseus. Here are shown as point-like sources. So we should be able to use this information, which is very different. This emission, you can see, is very different. The one from the AGNs from the cosmic rays and dark matter. And then combine this information of the model with the instrument response function to simulate the observation. Then we play the same game as we have played with Fermi-LAT. In the case we find no signal, so again, using as benchmark CS below 25, what we will do is what we have just done, basically put constraints on the dark matter model, so annihilation cross-section and mass in the case of annihilation, and lifetime of dark matter particle and mass of the dark matter particle in the case of decay. So this is how the analysis configuration is done. Again, we included all of the gamma ray sources. So for the dark matter part, we included min, med, and max for annihilation, and decay model for decay as the for the spatial part. For the spectral part, we will test different annihilation decay channels and different masses. And for the cosmic ray model, basically here we're using a combination of leptonic and hadronic annihilation models. It is called the baseline model. I can tell you a little bit more about it later if you are interested in it. But this is the baseline, so it will mimic the MED scenario, like the best guess scenario that we have according to data that we have. So basically, this model is also compatible with all the upper limits that we have from current and existing studies, like, for example, the observation that we have from MAGIC. And then the models that we use for the AGNs, that are basically the ones that were developed by the CTAO consortium from the paper of gamma ray propagation. And then, of course, the instrumental background that we have from being in the Earth, so for being an ECT. With this, basically, we construct the most realistic physical scenario, but this means that we have 8 fitting parameters in total, which is kind of a lot. And also, including this as a novelty, basically, we are using, taking profit of the huge field of view that CTA will have. So we will apply for an ACT the template fitting analysis. So basically, we are using these different templates, and we use template fitting analysis instead of going for the standard on-off analysis that is used in ACTs. So this is more or less the same that I told you now. And unfortunately, we are not expecting to find dark matter from the observation of Perseus galaxy clusters. So what we did is to put, confidence level upper limits. So let's take a look at this. In the plot in the left, we show the case of fitting annihilation main model to tau plus tau minus signal. And what it seems that we'll be able to assess is to explore this new range of parameters when it comes for the search that has been done in galaxy clusters. So basically, this will be the most constraining bound that comes from the search in galaxy clusters that will come from the observation of Perseus galaxy cluster in CTAO. But this line needs to be taken with a pinch of salt, because this is for the main model, but then what happens if we move to a mean model, so basically not including substructure, to the main model, that is the one shown here, and to the max model, basically the largest amount of contribution that we expect from substructure, and this will be the case, no? And we can see that we have basically a 2 orders of magnitude of uncertainty here. So this means that in the future, we need to put a lot of effort to try to assess how this uncertainty can be reduced, or at least how we can take it into account, because this introduces a lot of uncertainty in our results. And finally, the most brilliant results, I would say, that come for the case of decay. This plot basically shows the lifetime of the dark matter particle versus the mass of the dark matter particle. Everything below these lines will be excluded compared to the plots short for annihilation. And once again, basically, in this plot, what we see is that from all of the studies that has been done looking for dark matter in galaxy clusters, we see with CTA we'll be able to provide the best constraints, but not only for the searches that come from only galaxy clusters, but basically from all of the searches and from all of the constraints that we have from the dark matter lifetime of sorry, of dark matter particles. With CTA, we'll be able to test and explore, for example, with PV and annihilation channel, this new space that has been completely unconstrained. So trying to wrap up, basically, we are still having parameter space to look for wind dark matter. This is not something that we need to leave and completely obliged. Galaxy clusters are among the best targets to look for dark matter-induced gamma ray emission. Again, this search needs to be complementary to other targets. This is absolutely key. In the last years, it appears that how we made the analysis, it appears to be a tendency to find a hint of signal from the data that we have from Fermi-LAT, ranging from significance to 2.5 to 3, in accordance with what we have seen before and in accordance with the analysis that we have made. Something to do in the future, basically, that is something that I mentioned, is that in our analysis, we did not include the expected gamma ray emission from the astrophysical counterpart, so from the cosmic ray counterpart. This is something that we are exploring now, because, again, for that matter, putting it into contrast with the actual results, it doesn't seem to match. And then we have the future with CTNGO, which is very promising, not only to put dark matter constraints, but maybe we are able to get also this robust detection of the diffuse gamma ray emission signal from the astrophysical counterpart. So I guess this is everything I wanted to tell you. Thank you very much for the attention, and thanks again for the invitation. I will be gladly taking any questions.
Thank you. Any questions? So I guess I can start. Can you go back to when you were talking about your sub-halo modeling? Um, so because here, yeah. So I guess the first thing is just regarding the dependence of the concentration on the position within the cluster. Is this basically just stripping? Like if they're closer to the center, they just get more stripped, so they end up, I guess, more concentrated.
Exactly. This is the dependency that we have on the concentration.
Yeah.
So the baseline start is subhalos are from starting more concentrated than inhalos because they were formed in early stages of the universe. So from starting, they are more concentrated than the main halos that are from later in this evolution. But then, of course, the dependency of the position is just this tidal stripping process.
Mm. And so these simulations that you're drawing this parameterization from, so these are fairly old now, that these M-body simulations like Via Lactea and Aquarius. Do you know if this is something that hydrodynamical simulations observe any differences? Or, I mean, are there hydrodynamical simulations of galaxy clusters at the resolution you would require? Do you know? Because I mean, has there been any evolution from this knowledge from the sort of late 2000s until now?
That's a very interesting question. And in fact, we have hydrodynamical simulations. The problem is the scale. So the hydrodynamical simulations that are running to try to address these effects, basically, if the population are for a lower scale that is not a galaxy cluster.
Yeah.
So this is something that we need to explore further, if how this can be evolved, because the problem is that when you really want to go to these details of hydrodynamics, you really need to go to lower scales, but otherwise in galaxy clusters, you need to go to larger scales. So this is something that we have debating on in the last months to see if we are able to get any news from this part.
And maybe I just ask one more on that because it's maybe related. So can you go to where you're talking about just the the model for that, the halo itself rather than the subhalos. Just to refresh my memory how this was done. Um, so you basically have an NFW profile with a concentration. I guess maybe that's all the information that you need, but I guess for these galaxy clusters, there is like there will be some like lensing data, right? So you might be some constraints on the mass and the shape from that. Is that sort of folded in here somehow in the virial mass estimate or something like this, or how much information is coming from observations of these galaxy clusters? I guess is my question.
So this is an extremely interesting question. Let me see, because I think I have something in the backup. So let me see. Maybe not. Okay, maybe not. Okay, so basically the problem here is the kind of clusters that we are interested in to looking for gamma ray annihilations, because we want to look for clusters that are close to us. That means that they are so close to us that they are not able to produce lensing. So we
Okay.
don't actually have data for the mass of this cluster that comes from lensing. This means that we need to rely on the estimates of X-ray surface brightness. Basically, from the X-ray information, then we assume hydrostatic equilibrium, and from this hydrostatic equilibrium, the value of the mass is derived.
So do you
However,
not even
this
have like weak lensing? Is it just, are they just simply too close to have any? Wait,
for
yeah,
the
I guess
ones
it's
that
a
we
geometrical thing. Yeah.
from the ones that we explore is not the case, but let me see if I have something, because this is also a key point for us, because if we build all of the dark matter model based on the estimation of the mass of the galaxy cluster, this means that is one of the main uncertainties that we have from our analysis, no?
Mhm.
However, here, exactly. So basically what we did is to try to encapsulate also the uncertainty that we have coming from the estimate of this mass. This is the case for Perseus, if I'm not mistaken, yes. So basically, it's known that when we are comparing the value of the mass estimate from a galaxy cluster from these different methods, when these different methods are available, we see that there is some kind of bias. In the case of measuring the bias from the hydrostatic mass estimate, that is the one that we use to other methods, we call this the hydrostatical bias. So basically what we did is to explore different values for this hydrostatic bias that are showed here basically, and then to compute the value of the J factor depending on the different values that we have from the mass, and then to measure the scatter that we have on the J factor.
Okay.
And basically, for the case of the annihilation for the J factor, you can see the difference, this difference in mass is only sizable when we actually combine this this hydrostatic mass bias with the scatter that we have in the relation of the concentration mass relation. So then we start having some sizable contribution here, but for the rest of the case, the value seems to be negligible to
I
us.
see. Okay. Yeah. Thanks. Chris, do you want to go next?
Thanks. Uh, so, with the kind of contribution of the cosmic rays, are you actually trying to model that explicitly as a background?
Yes, in fact, I mean, since we are trying to look for gamma ray emission from dark matter-induced processes, either it is annihilation or decay, what we did is to include this template, this emission from cosmic ray as a background.
All
So
right, I
basically,
see.
the only signal that we look for in this part of the analysis is dark matter. In the paper here, basically, is divided in two parts. The first part, which is actually devoted to find this cosmic ray signal as a signal, and then the second part, which is basically using this model as a background for us.
So this is for the CTA. What about the Fermi? Did you look for cosmic rays in the Fermi data as well?
Yes, so this is something that we are actually doing, because we didn't include the cosmic ray modeling for the 49 clusters that we have, because it was kind of tricky. We know that clusters are somehow self-consistent objects, but this is something that we are exploring actually now. Basically, we are building gamma ray induced models from the cosmic ray population that we take from the 49 clusters, and then we will see if the Fermi-LAT data is compatible with it or not.
Thanks.
Thanks.
Anyone else? So maybe I can ask one. Maybe just it extends a little bit beyond sort of what you've been discussing, but in terms of just the future, like I definitely heard people say that CTA will be a sort of definitive test for the kind of thermal WIMP paradigm over some mass window. So your projections here are still maybe like just to like maybe 1 or 2 orders of magnitude away from the thermal, and I guess this is for a specific observation, right? But is there how much more data is required to bridge the gap down to the thermal cross section, just in sort of general terms?
So for the case of Perseus, I don't think we have a number of data that really can go much below. Here, if we want to prove thermal Rayleigh cross section with CTA, the main object to target, let me see if I have here, no, or maybe yes. Here, okay. It's basically to focus on the galactic center.
Oh, I see. Okay, so they were really talking about a galactic center
Exactly.
search for that. Okay, yeah.
Exactly. With the searches, with the prospects that we have for the galactic center, depending exactly on the annihilation channel, but also exactly on the dark matter profile that is used to model the galactic center. There was this work made by the CTA collaboration, basically by Christopher Einer and Gaby Zacharias here in University of Nova Gorica, where basically you can see that even taking into account all of the different astrophysical gamma ray emissions that we have in the galactic central region, and also taking into account the systematics that we have also from the uncertainties of correlating the instrument response functions, we should be able to explore, depending exactly on the setup, this part of the thermal wind cross section.
And 525 hours, I don't have a good. Is that a long time?
Yes.
It's many hours, but
It is a lot, but I can tell you that the first few hours, like let's say like the first 100 to 150 hours, will be done during the first years of operation of the most simple configuration that CTA can have.
It must be a high priority target, right? The galactic center for CTA.
It is because even though the best observation point for the galactic center is in the south, and the south part of CTA is still in construction, we can already say something using the northern array. So it will come during the first years of the what we call the alpha configuration.
And for these masses, you're not so affected by the Fermi excess, right? It's too low energy, so you won't have anything from any issue with that.
Exactly. It's too far to the right.
High
energies.
Cool.
It's very exciting.
Yeah. So maybe, okay. Well, thanks very much. If anyone has any final questions, now's your chance. But unless I see some hands, which I don't, I'll stop recording. So.